So now that we've learned a little bit more about the calculus of parametric curves, we can go on and talk about the arc length and surface area for parametric curves. I will remind you, arc length is tested on the AP exam. It's there. It's not a major topic, but it definitely shows up. It's something that you should expect to see in each exam. Surface area, on the other hand, is very much an extension. I do not expect that we will see surface areas of revolution for parametric curves, but while we're here, it takes very little time to add it on so that you're aware of it for your future studies. So first, arc length. The length of a parametric curve given by x of t and y of t on the time interval from a to b is given by this integral. And this integral should be really familiar looking. Like if you understood the way that a rectangular arc length formula worked, this should make perfect sense. In fact, this one's actually nicer because you can see that Pythagorean feel to it. We're taking the dx and squaring it. We're taking the dy and squaring it. We're taking the square root of that and we're just adding them up. Like in my opinion, the parametric form for arc length should be even easier to remember and use than the rectangular one was. So there it is. So now as we move on to surface area, I really hope that you guys recognize the similarity between these formulas and the ones we had for rectangular. Remember that the deal behind rectangular was that we're effectively just integrating the 2 pi RH formula, the surface area of a cylinder, right? So you still see there's just 2 pi here. At the end of it, there's still the arc length formula, which sort of represents the height of the cylinder that we're using. And then the radius in this is actually easier to deal with than it was, well, a little bit easier to deal with than it was in the rectangular, because we just need to think about whether or not this is the y function or the x function being used. So imagine that you have some parametric curve that's being revolved around the x-axis. If I'm revolving on the x-axis, then my radius is going to be whatever the y function is, and that's why there's a y here. However, if I'm taking a curve and revolving around the y-axis, in this case the radius of my revolution is an x distance, and that's why there's an x here. Otherwise, the structure of these integrals is very, very similar, right? So these are how we do the area of a surface of revolution when the curve is given in parametric form. So now we'll do one example here, and part of it I want to do by hand, so we'll do the arc length by hand, and then we'll use a calculator to do the surface area computation. So I want to consider a parametric curve given by x is t plus 2, and y is the natural log of secant t. I want the length of that curve on the time interval from 0 to pi over 4. So pause the video for a minute, at least set up that integral, and maybe think about how you might do that integral, but at the very, very least set it up. Right, so to find my arc length, I'm going to do the integral from 0 to pi over 4 of the square root of dx dt squared, so that's 1 squared, plus, now the derivative of the natural log of the secant of t. That'll be 1 over secant t times secant t tangent t. So the secant will divide out to 1 and just leave me with tangent t. So we have tangent t squared dt. So my arc length is the integral from 0 to pi over 4 of the square root of 1 plus tangent squared t dt. And if you haven't given some thought to how you're going to integrate that, sort of, pause the video and think about that, because I do want you guys to try and come up with that on your own. It's a reasonably basic integral if you have your integral formulas memorized. The short of it is that 1 plus tangent squared t becomes secant squared t, and when I take the square root of that, I'm going to end up getting just the integral from 0 to pi over 4 of secant t dt. Right? Well, the integral of secant t is the natural log of secant t plus tangent t, which just gets evaluated from 0 to pi over 4. Okay, so now I just have to do this evaluation. So let's see, we'll switch to, we'll keep using blue. So this is going to give me the natural log of the secant of pi over 4. It's 1 over the cosine of pi over 4, which is the square root of 2, plus the tangent of pi over 4, which is 1, minus the natural log of the secant of 0, so that's 1 over the cosine of 0, which is 1, plus the tangent of 0, which is 0. We end up on this part here just having the natural log of 1, which is 0. So that means that the length of this thing is just the natural log of the square root of 2 plus 1. So that's my arc length. Okay. And the next part of the question asked us to use the calculator to find the area of the surface generated when the curve is revolved about the y-axis. So if I revolve around the y-axis, it means I'm supposed to take this thing, like when, and sort of what I'm hoping that we're going to do here is we're going to imagine if I have a curve and I'm revolving it around the y-axis, the radius of the revolution is going to be x. So I need to have my x function, which, looking back at this thing, my x function was this t plus 2. That's the thing that I need to have, that I need to be working with when I'm doing my surface area computation. Right? So let's see if I can get myself a little bit more space to work with here. Okay. So what I'm doing is I'm effectively taking this integral setup, my arc length setup, right, and I'm applying this to the front of it, right? So when I'm doing my surface area, I will have 2 pi times the integral from 0 to pi over 4, kind of an ugly pi over 4, of t plus 2 times this integral setup. Now keep in mind, any way that that's been simplified we can use. So I should just be able to apply secant t to the end of it. This is the integral expression that I'm going to use. Now I just need to throw that at the calculator. So what I ended up with here for the surface area was 13.376 square units. Okay. As a reminder, I know this is sort of a messy page. As a reminder, it's really the arc length, really the arc length and the setup of these integrals that's most important. Being able to compute the surface area and even knowing the surface area formula, slightly less important. I'm really putting that in there for you guys to have as a future sense towards other math classes you may be doing. I do not think that it's going to be tested at all on the AP exam.